In this video, we're going to look at some problems involving exponential growth and decay, specifically looking at some application problems. Before we get into application problems, let's first look at a non-application problem. In this case, find the solution to the differential equation subject to the given initial condition, y equals 2.6, x equals 0, differential equation dy dx equals negative 0.82y. So in this case, this is negative 0.82 is our k value. Let's make a little note here that since k is less than 0, we have exponential decay in this problem. So as x gets bigger, the function values are getting smaller. They're approaching 0 in this case. So we can use our formula that the solution to this is going to be c e to the kx. K is negative 0.82, and we have x as our variable. The initial condition, which we could also write as y of 0 equals 2.6, is how we're going to solve for c. So we can plug in y is equal to 2.6, c, e to the negative 0.82, and then plug in x equals 0. This will give us 2.6 equals c e to the 0. E to the 0 is just 1. This will be 2.6 equals c. So our solution here is going to be y equals c, which is 2.6, e to the negative 0.82 x. All right, now let's look at some application problems. First one is a bank account that earns 5% interest compounded continuously has an initial balance of 0. Money is deposited into the account at a continuous rate of $500 per year. And I'm going to break this up into two separate problems. Our first problem is going to be when we don't include the $500 per year. And then we're going to include that and see what happens. So first, if we don't include it, then all we're doing is we have that the balance B is going to be increasing at a rate proportional to the balance. This 5% interest is our proportional growth, our exponential growth. And we can write that part as, first of all, the derivative of B, looking for the rate of change of the balance B, is going to be equal to 0.05 times B. Note that the 5% interest, we're going to write that as 0.05 using the decimal form for that percentage. And if we don't include the plus $500 per year, that's all we have for that differential equation. In fact, we can write this over on the other side as well, as we will have that as part of our equation. All right, if that's all we have, dv dt equals 0.05b, then our solution here would be b equals a constant c times e to the 0.05t. And since the initial balance is 0, then we can solve for c using that information. And this would actually give us b is equal to 0 e to the 0.05t, which is just 0. And let's see if that actually makes sense with the problem we're given. If we earn 5% interest on a balance, or but we don't add any money into that account, we're gaining 5% interest on a balance of 0 each time. That's not a very interesting solution. That's 0. If we started with some amount of money, if we had an initial balance of maybe 500 instead, then this value would turn into 500, and we could deal with that as well. All right, that's not the purpose of this problem. The purpose of this problem is looking at what happens if we add the 500 as well. So this added $500 per year, we know that we can write that as just plus 500 into the differential equation. This is saying we grow 0.05 times the balance, and we also add $500 per year. What we're going to do before we look at the solution to this is we are going to write this as 0.05 times just something. That's going to be B plus $500 over 0.05, or dB/dt is equal to 0.05 B plus 10,000. Now the reason we're going to do that is because now we can see that we have something similar to our exponential growth, where we're going to think about B plus 10,000 as our value of B, and we're going to do it in the same kind of way. This is foreshadowing what we're going to do in the next section, in section 9.5, but we're getting kind of a feel for it in this moment. So what we have here is, if we follow the same kind of steps, our solution, in this case, not just B, but B plus 10,000, is going to be a constant C times e to the 0.05t. That B plus 10,000 is just representing our B in our previous problem, and we can write this as B is equal to C e to the 0.05t minus 10,000. And this is our general solution. If we want to find the particular solution, we can solve our initial condition, which is that at the very beginning, B of 0 is 0. So we're saying that when B is 0, t is going to be 0, and we have this minus 10,000. That's going to give us that 0 is equal to C minus 10,000. So C is equal to 10,000. So our solution here is B is equal to 10,000 e to the 0.05t minus 10,000. And this is our particular solution that we are looking for in the problem. So the only real difference in this one is the initial differential equation and the fact that we're going to look at this B plus 10,000 as our just B value instead, or just our Y value. All right, our next application problem has to do with half-life. So here we have the radioactive isotope carbon-14 is present in small quantities in all life forms, and it's constantly replenished until the organism dies, after which it decays to stable carbon-12 at a rate proportional to the amount of carbon-14 present, with a half-life of 5,730 years. We're going to let C be the amount of carbon-14 present at time t, and we're going to look at this differential equation. So let's go over this problem. There's a lot of information here. Let's kind of talk about what's really needed and what's not really needed. The first part of this question is just giving us information about what we're kind of dealing with and filling in some loopholes about some more difficult kind of problems. It's really just a lot of information to say that this is going to work out the way that we want it to work out. It's going to constantly replenish till the organism dies, means there's not an extra variable we have to deal with of it maybe decreasing while it's living. And then it's just kind of setting up the problem. So I'm not going to worry about that first chunk of the problem really at all. I'm going to focus on the next chunk. All right, this rate proportional to the amount of carbon-14 present is why we have the differential equation C prime equal to negative Kc. That is where that's coming from, that proportional rate. And note that this is a negative K value because we are looking at decay. The amount of carbon-14 or carbon-12 present is going to be decreasing as we go forward, as it's going to decrease. What we really need here is the idea of what half-life is. So half-life is the amount of time, so it's a unit of time needed for something to become half of what it originally was. That's half-life. The idea is if you have a half-life of 2 years of something, then after 2 years, it has half the value it originally did. After another 2 years, it halves its value again, and so on and so forth. In this case, it takes 5,730 years to have a half-life, to get half of what it's originally there. So we're going to use that information to find K in this equation. We know that the solution to this equation is going to be C is equal to some constant, we'll call it C1 here, e to the negative kt. And we need to find what is the value of k. Note that C1 is the initial value, or the initial amount present. Actually, I'm going to call it C naught instead, C with a little 0 underneath, because it's talking about when t equals 0, that's that value. So let's set up an equation here that we can find the value of k. And we're going to do that by finding t, or by plugging in for t. We know that when t is equal to 5,730, c is going to be equal to the initial amount divided by 2. We've halved what we've had originally. So this will give us an equation that we have C naught divided by 2 is equal to C naught e to the negative k times t, which is 5,730. And now we're going to solve for k. So we can do that by dividing by C naught on both sides. Note that's going to cancel that C naught out completely. And we'll be left with 1/2 equals e to the negative 5,730 k. Then I'm going to take the natural log of both sides to get rid of the e. This will give us natural log of 1/2 is equal to negative 5,730 k. And finally, we're going to divide by negative 5,730. So k is going to be natural log of 1/2 divided by negative 5,730. And note that that's about 0.00012. So that is a rate that we are talking about. It is decreasing at that rate proportional to its original value. All right, now that we have this value k, let's think about how we can use this to answer a question. So in 2014, scientists found that an old relic made of cloth contained 91% of the amount of carbon-14 contained in a freshly made cloth of the same material. And we can use that information to determine how old is that relic that we found. So we're saying when it's freshly made, it has 100% of the amount of carbon-14 present. And then in 2014, we now have 91% remaining. Since we know the half-life is 5,730 years, since we have this value of k, we can figure out the value of t. And we're going to set up a similar kind of thing here. We have c is equal to c naught e to the negative 0.00012 t. And what we're saying is that c is going to be 91% of c naught. 0.91 of c naught. It's almost all of c naught, but it's not quite all of it. And if we plug that in, we have 0.91 c naught equals c naught e to the negative 0.0012 t. We can divide out the c naughts, and we'll be left with 0.91 equals e to the negative 0.00012 t. And we can solve for t in a very similar fashion as we did before. We can take the natural log of both sides, get natural log of 0.91 is equal to negative 0.00012 t, and we can divide by the negative rate, get natural log of 0.91 over negative 0.00012, which is about 786. So our answer is about 786 years old. All right, there's a lot of stuff going on here. It's all based on this idea of the proportional growth or decay. We can build our differential equation, build our solution, and then we can play around with that in a lot of ways. In fact, a lot of what we did here in this problem is a pre-calculus problem that's wrapped up in this differential equation. The brand new thing here is using the solution of the differential equation. And I'm trying to show a couple more difficult problems in this practice video. So maybe the problems in the homework will not be as bad.